Okay, so we are going to talk about the transformer because, as I mentioned in the first lecture, so we're going to focus on transformer because that's a hottest thing in computer vision and deep learning. So I'll give you a very broad introduction so that you understand the basic, then we are going to go in detail in the papers. So we'll talk about what is transformer. In particular, we'll talk about what is self-attention, because that's a main component of transformer. And self-attention has the query, key, and value, and position encoding, and encoder-decoder architecture. Okay, so transformer essentially is used for modeling the long dependencies between input sequence elements. It supports the parallel processing of sequence. So in a way, it's LSTM will process a sequence in a recurrent network, but the main difference is that the transformer we can do in parallel. It doesn't require any inductive biases, so therefore it can be used for multiple modalities. We can apply for images, video, text, and speech, and it will have similar actually processing blocks. For example, transformer started in the natural language processing, but it's widely used in computer vision. So typically, transformer is pre-trained in a self-supervised manner on the very large data set. So that's one limitation, that needs a large data set to be trained. And the performance has been excellent, and it can scale to very large capacity dataset networks for the huge dataset. So transformer has been used for recognition tasks like image classification, object detection, action recognition, segmentation. We're going to discuss more in detail. It can be used for generative modeling, used for multimodal tasks like visual question answering, visual reasoning, visual grounding, and it can be used for video processing, activity recognition, video forecasting, and the low-level vision like super resolution, image enhancement, colorization, and also 3D analysis, the point cloud, like LiDAR data, object detection, tracking, and segmentation. So in natural language processing, because transformer started from there, it has been widely used model called BERT, which is a bidirectional encoder representation from our transformers. It has been used in GPT, which is very popular in the media, you must have seen. So generative pre-trained transformer, they have different versions, version 1, 2, 3 from OpenAI. And another model is called Roberta, robustly optimized BERT pre-training, and then a T5, text-to-text transformer, and so on. So just a simple introduction to BERT. So it is encoder representation and used for the natural language processing. So original transformer will attain only to the context on the left of a given word, because we'll learn this is used for the machine translation. So it will look at the particular word and all the words it has seen before, but not the words on the right side. And that's what the BERT does. So that's why it's called bidirectional, and it improve the learned representation. And it is used on the two pretest tasks in self-supervised manner. So one is called mass language model. So what you will do, you will take a sentence and remove 50% of words randomly and train it so that it can predict the mask words. And in predicting the mask words, it will learn, it will incorporate a bidirectional context from the left and the right. And other pretest task is next sentence prediction. So in this case, we were given a pair of sentences, A and B, and will predict that whether this pair is valid, that they appear, next to each other. And then, the way they do it, that they will take the 50% of time, they will take the actual sentences, and the remaining 50 times that they'll take B will be just random sentence, so that, it can be able to distinguish that it's a real pair and it's not. So publications in transformer has been really impressive. It's a big breakthrough, and it started in NLP, but it is, a lot of interest in computer vision community. That's why we're discussing. So this is kind of graph shows that 2017 to 2020, these are number of publications, as you see how it's going up. So there was just transformer, then a BERT, and Roberta, RT5, GPT-3, and all those things. Then if you look at the archive papers, this is also a huge increase over the years. And then if you look at the keywords, then it started mostly in 2018. Mostly it was self-attention and transformer. Then BERT came in 2019, and 2020, a lot of these transformer, and then BERT and so on. So that's the way it's going. And this, by the way, is these things are taken from our survey paper I mentioned to you the first lecture. And so now transformer, it consists of encoder and decoder blocks. And main component of each block are self-attention, layer normalization, and feed-forward network. Okay, so just keep in mind. Now, main difference of the self-attention with the CNN is that these filters are dynamically calculated. They depend on the data. So that's the main thing, because in CNN, once you learn, these filters are fixed, regardless of what is the input. So the transformer components are, first one is self-attention. So we have query, key, value. We multiply these, scale it, to normalize, and sometimes we mask some, but right now you can ignore this. And then we multiply this attention with a value, and we get a better representation. Now, this self-attention, we can have multiple heads. So this is one, and then we have second one, third one, and we'll repeat the same process. Query, key, value, the same here, and then we'll get output from multiple heads, like here, and concatenate, then we'll combine them, and we'll go and talk about that. So it's multi-head attention. Now, this is the encoder of the transformer. So we'll have input, we'll do the embedding, and we are going to add the position encoding. Then this is multi-head attention, which is explained here. Then we will do the skip connection. We will take this one and add it after the multi-head attention, which is called add and normalize. Then we'll have fully connected layer, and then we'll have again add and normalize, and we'll get this output of encoder. Now then that goes to the decoder. This is a decoder. Decoder is fashion very similar to encoder, as you see the same blocks. So now decoder will have the input, which is coming from the output of the decoder. So it's right shifted. And also, so that goes here, then again embedding, then we have multi-head attention, key, value, key, query, position, encoding, add normalization. But decoder will have also input from the encoder, so which is coming here. And so that will have multi-head attention, add normalize, fully connected, and normalize, and so on will come out. So that's the transformer, okay? So now self-attention is very important concepts, and so we want to explain that different way. So, and by the way, I have leveraged the slides from lots of different people. So that's a great thing which has happened with the internet boom and interest. There's so many people working on these, and they are spending so many hours preparing these nice presentation videos, and all other people can leverage. So instead of me making these new slides, so I'm taking there, and I want to thank all of them people, and I'll acknowledge these people where I've taken slides. So just simple idea of self-attention. So let's say we have these words: hi, how are you? Okay, so each word is a token. It's called token, and we will come up with representation of each word, which we call embedding, and we will have a vector which will represent hi, another vector represent how, and this will represent R and U. So this embedding is called word-to-vec, and there's many other representation. Word-to-vec. So we take a word and map it a vector. Okay. So simple word-to-vec can be, say you have 5,000 words in your vocabulary. So you assign a number to each of the word, and that's your representation. But there are much better way to do that. So let's assume you can have for each word a vector, and this vector can vary length, whatever you decide. So self-attention, what it does, that it come up with this attention matrix, self-attention matrix, and that is nothing but taking the dot product of this first word with itself, then second word, and third word, and fourth word, and that becomes this row. So as you see that, suppose the word-to-vec representation like this one for this word, and word-to-vec representation for the second word like this. So we'll find a dot product of this, and that will go here. And we'll same thing, we'll take this vector and dot product with x3 will go here, and we'll take this one and dot product with x4 will go here, and we'll repeat for the second word, third word, fourth word. So this is the attention matrix. Now it may look like this: so x1, x2, x4. So these are the the dot product of correlation between x1 and x1 and x1 and x2 and so on. These numbers are like that, but you understand the idea. So then we are going to normalize and so on. So then what happens, that given this attention matrix, we are going to take our original embedding of these four words, and we'll transpose those, and we'll multiply each of this word with the attention matrix, and we'll get the y, which will be the w, which is attention matrix, multiplied by x transpose, we'll get. Now this representation is after self-attention. This was before. So that's what the self-attention is doing. Because as you see that what we have done, that in order to get this new representation, we are getting the contribution or context from all other words. As you saw here, that we are doing the dot product of this word with this, and this dot product of this word with this, and so on. So it is using a context. I mean, we can just individually represent each word. That's what we have done in the beginning. But using this attention, we are getting the context, and then this is a better representation. So that's a self-attention in terms of the words. So please feel free to stop me. Don't check, but just start speaking so I can help you. Any questions so far? Okay, so let's now continue. So our job is to do the self-attention, the images, okay? Because images are 2D. So let's say we have 3 channels, our feature map, or you can even consider this as an RGB image. So we have very small image, 3 by 3, and we have 3 channels, RGB. So self-attention, what we want to do, that we want to take this feature representation, we want to come up with a better feature representation here, as I explained to you what we were doing for the words, okay? So now, same idea that we will take these and we will multiply with the key, we'll get this. We'll multiply with the query, we'll get this. These are the matrices or vectors and values. So from the original one, we'll get a key, query, and value. As we did before, we're going to transpose the key and then multiply with the query. We'll get this, we'll do the softmax, and this will give us a tension map, okay, as I explained to you before. Now, after that, then we'll get the value and then multiply with the attention matrix, we'll get this back here. So as you see that to get the key, query, and value, so we are doing this one by one convolution. And these are the parameters which we are going to learn. These convolution parameters for this one, and this one. There are 4 convolution parameters. So we can look into a little detail. So we have a sequence of entities. So these we'll call entities or tokens. So now it's better to understand that we have 9 tokens. Okay, so this is one token, another one, second one, we are 9, 3 by 3. And this token is the 3 values. Value here, value here, value here. Okay, so this one token, second token, third token. So we have n token, n in our case will be, 9. So, but this is general, so we have n tokens and each is a d-dimensional vector. Okay, so now as we did before, we are going to take this WQ matrix and WK matrix and WV matrix, and we are going to get a query, key, and value. And so these will be the dimension of the WQ matrix, D by DQ, and D by DK, and D by DV. And we're going to assume that, DQ and DK are same. So then what will happen, that we take a X, multiply with WQ, we'll get a Q, and X multiplied by WK, we'll get K, which is key, and similarly, we'll get a value. Now, once we have these 3, then we are going to do this. We're going to do the Z. So we'll take the Q from here and K from here, transpose it, and multiply. And this will give us a tension, as I explained it here. Then we multiply with V. And of course, we'll do the softmax to normalize. So that is the idea of the self-attention in an image, okay? Now, you need to be very careful about these dimensions. And I think even this figure has problem, so I fix it. Now this attention should be 9 by 9, not 3 by 3. Okay, so let's look at more carefully now for this particular example. So we have X, and so as we say for this example, we have 9 tokens, 9 pixels, and each has 3 dimensions. So D is 3, N is 9, okay? Then for our case, the WQ will be 3 by 3. So we are assuming that, because we want 3 back here. So D is 3 and DQ is also 3. And same way, WK will be 3 by 3 and WV will be 3 by 3. So now when we get this QKV, we will find out the Q will become 9 by 3 because X is 9 by 3 and WQ is 3 by 3, so it will become 9 by 3. And same way, K will be 9 by 3 and V will be 9 by 3. So now when we multiply Q with K transpose, that will become 9 by 9 because Q is 9 by 3 and this transpose of this will become 3 by 9, so that will become 9 by 9. That we can multiply with 9 by 3, which is V, then at the end we'll get 9/3. And that is Z. And as you see, that's true because we have 9 tokens here, and each is 3 dimension. So, which means the attention matrix 9/9, which is this one. And then we have these matrices. WQ is 3/3, so which is 9 elements, 9 unknowns. That's what we want to learn. We want to learn 9 here also, and we want to learn 9 here also. And then at the end, we will have 9 here also. So now if you look at this one, and that's true, because when we are going to get this channel from these, we are going to apply 1/1/3 convolution to this tensor applied. Each pixel will get the first channel. To get this one, then we'll apply again 1/1/3 to all these 3. We'll get second channel, and then we'll have third channel 1/1/3. So there are 3 convolution, and each has 3 parameters, so there'll be 9 parameters, and that's why this matrix has 9 parameters, so 3/3. And same way you can see that this will be also 9 parameters, and this will be 9 parameters also. So then I think it's very nice. This figure explain that this is what we are going to do in the self-attention. Okay, any question, please speak.
Yes, Dr. Shah. So
Yeah.
Why are they given the names like key, query, and value? What does it mean?
Yeah, it's you know, we'll find out sometime. You will have the query. You want a query given the image, and you want to find out what object it is. So these are the 3 different versions of the same thing, and we essentially want to find out the global correlation, because typically when you do the convolution, you apply, say, 1/1/3. It's just looking at only this pixel. But what, as you see here, that when we do this, we are going to look at all of these pixels. So that's a main thing, that global context. And in order to get attention, maybe you have to have this something like, you can call something any other name, that's fine. But we want to get this one. Once we get attention, then we want to apply this to every one of these. So the reason we are doing these things, because we want to have some learning. We want to determine these. Otherwise, we can do that as we did in the previous one, in the language thing, as I give you here. Now there was no learning here, right? We just took this one and we multiply, we get this one. So there was no learning. Okay, we did a transport. It's nothing. But the real thing in deep learning is that we want to learn something, and that is the main point. Okay. So that is our self-attention for images. And so now let's continue. So this whole idea came from the paper, Attention is All You Need. It was published in 2017 by these guys from Google. And in 4 or 5 years, it has already have 34,000 citations. It's a big breakthrough. So now, rest of the presentation, I'm going to use, these are 2 valuable resources for the understanding transformer, especially this one, nice blog. And then actually there's a presentation from this professor. He just used this one to get the slides, and it's very nice slides, so I'm going to use those. So now this is a big picture. So this is a transformer. So, and we are going to go through the machine translation example. So this is French, I assume, and we want to get the English. And this is the translation. This is I'm a student. So we have the encoder. This is encoder. There are different blocks, and we have a decoder. So that is your transformer. So now each encoder block, as I mentioned before, has self-attention and the feed-forward neural network. Okay, so let's look at in detail. So we are going to take actually even simpler sentence. This just say 2 words: thinking machine. This first token, the second token. Again, we embedded it's word awake or something. This is a representation of thinking, representation of machines. Okay, so we are going to do in these 2 words, we are going to apply the self-attention. Now, after self-attention, we will get Z1 for this and we'll got Z2 for this. Then we will have the feed-forward neural network, and from Z1 we'll get R1 and Z2 from R2. So feed-forward, this is very simple, MLP. Okay, so that is, and now once we get this, that R1, R2, they'll go to next encoder block. So number 2, number 3, and we can have lots of these blocks. Okay, so now as you see that this feed-forward neural network is independent for each word. So therefore we can parallelize, we can do all simultaneously. Compared to LSTM, which is sequential, we'll do one word at a time. So that's the main advantage of the transformer. So now let's look at more in detail that we have 2 words. These are the embedding, and we are going to do self-attention. So as we talk about, we will take this WQ matrix, multiply with X1, we'll get Q1. Second word, we get Q2. These are the for each query. We'll get keys, we'll get values. Okay, so we'll have these 3 matrices. So you already know that. So that is the first thing. Now we'll create 3 vectors by multiplying input embedding and with these matrices. And this is what we are going to do, as I explained to you. Each of the word we multiply with this, we get that QI, KI, and VI. Fine, very easy. So once we have that for these, then we are going to proceed further, and we want to calculate a score to determine how much focus to place on other parts of input, because we have 2 words here, very simple case. So we want to find out how much context we want to put on this based on this one. So that's what we are going to do. As we did before, we multiply Q1 with K1 and Q1 with K2, because we are focusing on this word, as I showed you the correlation, the dot product. So let's say we get these values, 112 and 96, whatever they are. So these we will call the scores. And then once we have that, the next thing is that we are going to divide by under root of dk, dimension of the representation. So let's assume our length is dimension 64 in this case. So then that would be 8. We divide by 8. Each of these will get these numbers. And then we'll do the softmax. So that this should sum to 1. Okay. So now when we have that, then we'll take these and multiply with the value as we did before. So 0.88 multiply with V1 and 0.12 multiply with V2, that will become our Z1. So that's a process of applying this self-attention for the one word. X1 we started and we got Z1. And it's very clear the process we did. Same thing we'll repeat for X2 and whatever other ones you have. Okay, so that's it. So we took the Q, the query, 2 words, the key transpose, multiply, divide by under root, dimension, dk, multiply with V, and we get C. So it's very nice, very, very good. And I think these guys have done a very good job to explain this. Okay, now this was one head now, but we can have multiple heads. So what that means, we took the X, thinking machine, 2 words, and we said just one head. So one head we'll have 8 heads. So attention from head 0, attention from head 1, 2, 3, 7. Okay. So so the idea is that it will expand. I tried to change this, but then change again. So it expand the model ability to focus on different position. Okay, and that's the idea of using multiple heads, and I'll show you example. Then also it gives the attention multiple representation spaces, and because the whole idea of deep learning is that you want to learn, and if more parameters you have, you can learn more because you're determining that based on data and training. So what that means that now we will have, instead of 1Z, we will have 7Z, each Z coming from different head, 8 Z's from Z0 to Z7. So each Z coming from different heads. So we have 8 heads now, and each one is a 2, thinking machine. So then to combine that, again, we'll have another matrix, W0. We'll multiply with this, and we will get a Z. Finally, at the end, we'll have again just Z, which will use the multiple heads to get this one. So that's what we have. Okay, so now, these are the steps. So we have a sentence. We embed each word in the sentence. We split in 8 heads. We multiply X, which is the first head will be X input, and then other layers, blocks will be R from the previous one, and I'll show you. And then we'll calculate attention. Attention is nothing but query key value, and then concatenate Z, then multiply with W0 matrix, and produce the output of a layer. Okay, so here we go. So this is our X starting point. This is our first head, W0, W0V, W0K, W0Q. These are matrices which we learn. Then we get these query key value, and using that we get Z0, as I explained to you. So this first head, and then we have this matrix will multiply. This is our second head, third head, fourth head, and eighth head. So once we have that, multiply with W0, we'll get Z. So that's your multiple heads. So in the first one, we'll have X, but the other, layers, we'll have the R from the previous one. So now here's an example what these heads are doing. So what we are showing, only 2 heads. They are colored, this orange one and the green one. So this word it, as you see that there's attention being paid, animal referred to it. Okay, then tired, was, and so on is related to that. As compared to cross, there's not much attention being paid. And so this is for 2 heads. And then if you look at all the heads, then you can look at, how each of the head is paying attention to this particular word. But now we have attention to each of the word. We'll have something like this for all these words. That's why it becomes very complicated and a lot of computation. So that is the multiple heads attention. Okay. So now other important concept in transformer is what is called position encoding, which will represent the input order. And so that what we are going to do will add a vector to each input embedding, and that's called the position encoding. These vectors will follow a specific pattern, and that model learns, and this learned patterns will help us determine the position of each word and distance between the different words. So here's the idea. So again, this is your French. this is embedding, and suppose this is the representation. Now we are going to add to that the position encoding, and we'll add this and will become this. And this is what we are going to feed to the encoder. Okay. So now position encoding, so it will basically add a vector, and we will have this sine cosine pattern. And there are reasons, why we want to pick, but right now we are going to discuss, we'll get into that later. So, so what we are going to do, this W or omega will be given by this and will depend on the dimension of our embedding. So with large number and K defined like this. And so we will have alternate sine and cosine, and so it will look like this. So let's say our embedding representation, the feature vector, the D is 128. Then, and let's say we have 50 words, okay? So this will be position encoding for the first word. This will be position encoding for the second word, and so on. As you see that every word has different, encoding to distinguish that we have different words, and the reason that why we want to use this complicated way to determine. And so that is one way to do position encoding like this, sine cosine or some other one. Other way, actually, we will learn also this position encoding. So we don't have to do this thing. We'll initialize randomly position encoding here. These numbers will randomly initialize these, but these will become parameters of network. We'll learn that, and we're going to talk about it. Actually, these days people have found it's better to learn than do the fixed position encoding. Okay, so that's about position encoding. And so then this will become like this. We have thinking machine, we have position encoding, we get X1, X2, we know self-attention, we get Z1, Z2. And then the next steps comes in. So what we are going to do, we will have this skip connection. We take the X and add to Z, okay? And then once we add that, then we will have to normalize. That's why I'll add and normalize. Adding here and normalize, so that then it can go to the next block. So now for that, we are going to use what is called layer normalization, okay? So because it will normalize a feature across these features, so that then next encoder block will treat this similarly as the encoder block previously treating, because otherwise it will be a problem. So that's the reason we're going to do that. And you guys know batch normalization, you have done a lot, right? So this is our batch. We have these 3 samples, then we find the mean across each of the element and standard deviation. We subtract the mean and divide by standard deviation. That's called batch normalization. And layer normalization we do actually this way. So we take the mean and standard deviation for each of these, and then subtract the mean and divide by the standard deviation. And that's important. That will kind of treat each block consistently. So that is your normalization. And so then this is the transformer, full transformer. So we have the input, and this is, we add the position encoding, and this first encoder block, second encoder block, we can have many. Then we have this a decoder. So decoder will have position encoding, and then the self-attention and normalize, same thing. But then it will have the output from the encoder, which comes here. Because see that if you are doing machine translation, you have you encode the French, then you want to decode in English. So you want to get the output from encoder. And so as we say that we are going to, get the output from decoder and left shift and input here also. That's what this is. So then it's the same pattern. This decoder is very similar to encoder. There's all these blocks. So we get this thing. So here is the idea that we have the query from the decoder, and based on the key and value from the encoder, we will do the attention. And this attention is encoder decoder attention, because not all three are from the same embedding. The self attention we did was we're just taking the same word and we are getting 3 copies and so on. So here actually, in a way you can say is cross attention. You're getting from here and then to the key value from here. So that's the query is from the decoder. So then I think it's the same thing. So encoder, decoder, add normalize, feed forward, and keep going. So at the end, we will have linear layer and the softmax. So that is your transformer. So now, at the end, we want to do translation, right? So we want to find out which word in our vocabulary is associated with this index. So maybe it's 5. And the way we are going to do it, get this decoder output, linear layer, then we get these logits. So logits will be based on what's the vocabulary size we have. We'll get numbers, and we'll do the softmax, the normalizes, these probabilities, and we'll find out that word happened to be this 5, which is M. So then, again, recap: French, embedding, position encoding, encoder, key value, and here comes the previous one, because we are saying IM, so we already have I output from here that goes in the decoder and softmax, linear and softmax. So as you know that the output may be something like this, but then we want to do the probability softmax, so we have to normalize this and come like that. And the standard losses. So you guys have heard about entropy, which is the P log P, and that came from, and the cross entropy is 2 different distribution. This is the entropy, same distribution, P and log P. And here we have 2 distribution, P and Q, and we have PI and log QI. So one distribution is from ground truth, and other distribution is from what the network predicts. So that's why it's called cross entropy. So this, in a way, came from what is called Kale divergence. These were the guys who came up with this idea that you are given 2 distribution, how you want to find a distance between 2 distribution, how similar, dissimilar they are. So, so the way this works, that we take the PI, log PI, and log QI, we subtract that and we multiply by PI. So it's this entropy. So now what happened that when we train the networks, we actually are more interested log PI and QI, the difference between these. So that's why the cross entropy we use here. But it came from the Kale divergence. Now, as you see that this is not symmetric, because P and Q, difference between the distribution P and Q is shown like we do the difference between 2 distribution, log of that, but then we multiply by PI. So that's why PQ and QP will be different, where this will become Q. So then there's this Jensen symmetric distribution. So we combine that, we look at the P and Q, make it M, and we look at P distance M, and then Q and M. So these are different ways, loss functions you can use, and we'll learn more in detail. But just an idea that why we are using cross entropy, and the reason is that we are looking at two distribution. One distribution is from the ground truth, other distribution is from the network, and we want to minimize the difference between those distribution. Okay, so that's, I think, kind of end of this. So let me give you a chance to ask questions so far. Any questions you guys have? How do you put this thing? Okay.